Welcome to the deep dive. If you're seriously looking to get ready for that CSWIP 3.1 Welding Inspector Exam, well, you're definitely in the right place. Think of this as your kind of dedicated study boost. We're aiming to cut through the jargon, clarify those, tricky multiple choice questions.
Yeah, the ones that really make you think.
Exactly, and arm you with the confidence you need. We want you to really master the concepts, not just memorize facts.
That's absolutely the goal.
Yeah.
Because the CSWIP 3.1, it's not just about recalling information. It digs deeper.
Right.
It's about understanding why things happen in welding, why certain procedures matter so much, how to spot potential problems. We're building understanding here.
Couldn't agree more. So here's the plan for today. We're going to hit some core questions typical of the exam.
Okay.
We'll look at the options, pinpoint the correct answer, and then really unpack the reasoning behind it, give you that solid foundation. Ready to jump in?
Let's do it.
Okay, first up, a question about material science. It asks, cold shortness. Your options are A, is mainly caused by the presence of sulfur, SB, is mainly caused by the presence of phosphorus, P, is mainly caused by the presence of manganese, Mn or D, is mainly caused by the presence of silicon, Psi. What's the verdict?
Okay. For this one, the correct answer is B, is mainly caused by the presence of phosphorus.
Phosphorus, right. So what exactly is cold shortness?
Well, think of it like this. Steel suddenly becoming brittle, fragile, especially when it gets cold, ambient temperature or lower.
Okay.
And phosphorus, well, it's the main troublemaker here. If you have too much of it in the steel, it tends to gather at the grain boundaries, sort of like building weak spots within the metal structure.
Ah, right.
And those weak boundaries, they drastically reduce ductility, the ability to stretch, making the steel prone to cracking or snapping, especially in the cold.
So it's specifically phosphorus for cold conditions, different from other issues.
Exactly. There's something called hot shortness, which happens at high temperatures, and that's usually linked to sulfur. But for cold shortness, phosphorus is definitely the element you need to remember.
That makes sense. So knowing this isn't just like exam trivia, it's fundamental for knowing how a material will behave, especially in cold climates. You need to prevent failures.
Absolutely critical in real-world applications. You need to know what your material can handle.
Okay, great start. Let's shift gears now from what materials are to how we measure their behavior, specifically their ability to stretch. Got a calculation question for you now.
Okay, ready?
In an all-weld metal tensile test, the original test specimen's gauge length is 50 millimeter. After testing, the gauge length increased to 72 millimeter. What is the elongation percentage? Options are A, 44%, B, 144%, C, 69.4%, or D, 2.27%.
Right. The correct answer here is A, 44%.
44%. Can you walk us through how you get that?
Sure. It's actually quite a straightforward formula. Elongation percentage, it basically measures ductility, how much something can stretch before it breaks. Okay. The formula is, you take the change in length, divided by the original length, and then multiply by 100 to get a percentage.
Makes sense.
So in this case, the length changed from 50 millimeters to 72 millimeter. That's a change of 72 minus 50, which is 22 millimeter.
Great, 22 millimeter increase.
Then you divide that change, 22 millimeters, by the original length, 50 millimeter. So 22 divided by 50 equals 0.44. Okay. Multiply that by 100 and you get 44%.
Got it. 44%. So what does that number 44% actually tell us about the weld metal? Why is it important?
It tells us a lot. It's a direct measure of ductility.
Yeah.
High percentage means the material is more ductile. It can undergo significant plastic deformation, stretching, before it finally fractures.
So it's less likely to just snap.
Exactly. A ductile weld gives you warning signs. It can bend, deform, absorb energy. A brittle weld with low elongation might just fail suddenly. So 44% indicates pretty good ductility, which is often crucial for safety and structural integrity.
That's a really clear way to put it. It's like a safety indicator built into the material itself.
Right.
What happens if you get a really low number then? What's the immediate red flag for an inspector?
A low number, yeah, that's an immediate red flag for brittleness. It tells the inspector the material won't deform much before failure.
Right.
So it's much riskier in situations with impacts or vibrations or any kind of dynamic load. It concentrates stress rather than distributing it. Big concern for safety critical parts.
Very clear. Okay, moving on. We know about composition. We know how to measure properties like ductility. But sometimes we need to actively change those properties, right? Heat treatment comes in here.
Exactly.
So next question, normalizing. Is it A, fast cooling from the austenite region when applied to steels? B, is slowly cooled from the austenite region to approximately 680 degrees Celsius and then cooled down in air?
Okay.
C, is slowly cooled down in air from below the lower critical limit. Or D, none of the above.
This one's a bit tricky. The answer is D, none of the above.
None of the above. Interesting. Okay, so why are the others wrong, and what is the correct definition of normalizing?
Right. This highlights how precise you need to be. Normalizing is a specific heat treatment. You heat the steel above its upper critical temperature.
Okay, into the austenite region.
Correct, where the structure changes. Then, and this is key, you cool it in still air. Not in a furnace, not quenched in liquid, but just still air.
Still air. Why is that specific cooling rate important?
Because that controlled cooling allows a fine, uniform grain structure to form. This improves ductility, it improves toughness, and it also relieves internal stresses left over from manufacturing or welding. It refines the steel.
Got it. So looking back at the options, fast cooling in A sounds like quenching, right?
Exactly. That's for hardness, usually makes things more brittle. Option B describes a sort of partial cool, maybe annealing, but it's not the full normalizing process or temperature range.
And C, cooling from below the critical limit.
Yeah, that won't work either because you need to get above the upper critical temperature to transform the structure properly before cooling. So none of those definitions quite nailed it.
Precision is key. You mentioned cooling in still air. What if it's, I don't know, a bit drafty on the shop floor? Does that actually matter much?
Oh, it absolutely matters. Still air implies a consistent, predictable cooling rate. If you have drafts, different parts cool at different speeds. That can lead to uneven properties. Some areas might be harder or softer, more stressed or less tough than others. It basically undermines the whole point of getting that uniform, refined structure. You might not see it, but the mechanical properties could be compromised.
Wow. So even seemingly small details in the process have big consequences.
Definitely. Consistency is crucial in heat treatment.
Right. Okay, from controlled treatments, let's get back to the welding process itself. A practical question now. Is it permissible to allow a multi-pass butt weld to cool down between weld passes? Options are A, it should be up to the welding inspector. B, no, the weld must be kept hot at all times. C, it depends on the welder. Or D, it depends on the specification requirements.
This is a fundamental one. The answer is D. It depends on the specification requirements.
Specification, not the welder, not the inspector.
Absolutely not. This isn't a subjective decision. Whether a weld can cool between passes, and by how much, is strictly controlled by the Welding Procedure Specification, the WPS.
The WPS, okay.
That document is like the recipe for the weld. It's carefully worked out based on the material, the thickness, the joint design, the intended use, everything.
And it specifies temperatures.
Yes. Critically, it specifies the interpass temperature range, a minimum and a maximum temperature the weld area must stay within before the next pass is added.
Why is that range so important?
It controls the cooling rate. Too cold, and you risk things like hardening or cracking, especially hydrogen cracking. Too hot, and you can get undesirable microstructures, like coarse grains, which reduces toughness. Sticking to the WPS ensures the final weld has the right properties, strength, toughness for the job.
So the WPS is really the law here. But, in reality, are there pressures maybe to speed things up that might tempt someone to bend the rules on interpass temps? What's the risk?
Oh, absolutely. Time pressure is always a factor. Letting it cool too much takes time. Rushing passes while it's too hot might seem faster.
Right.
But the risks are significant. Cooling too low increases hardness, reduces toughness, ups the cracking risk. Letting it get too hot degrades toughness through grain growth. These aren't always obvious visually, but they create hidden weaknesses that could lead to failure later on. That's why following the WPS and inspection is vital.
Underlines the importance of diligence at every single step.
Every step.
Okay, final question for this deep dive. We've looked at materials, calculations, process control. Now, let's think about testing the finished joint. The question is, transverse tensile test, is it? A, is used to measure the ultimate tensile strength of the joint. B, is used to measure the elongation of a material. C, is used to measure the yield strength of a material. Or D, all of the above.
Right. For the transverse tensile test, the primary answer is A.
Yeah.
It's used to measure the ultimate tensile strength of the joint.
The joint specifically. How is that different from the elongation test we talked about earlier?
Good question. The earlier one was an all-weld metal test. It just tests the properties of the weld metal itself.
Okay.
The transverse tensile test pulls a specimen taken across the entire weld. So it includes parent metal on both sides, the heat-affected zones, HAZ, and the weld metal in the middle.
Ah, the whole assembly.
Exactly. Its main job is to find the ultimate tensile strength, UTS, of that entire welded joint. It tells you the maximum stress the whole thing can take before it breaks, wherever the weakest point might be.
So while you might see elongation or yield during the test, the main purpose is the UTS of the joint.
Precisely. You're testing the integrity of the complete connection, not just one part of it in isolation.
That makes sense. It gives you the big picture. Can you get situations where, say, the weld metal itself is strong, passes its own tests, but the joint fails this transverse test?
Oh, very common. The weld metal could be perfect, but maybe the HAZ got weakened or embrittled by the welding heat. Or perhaps there wasn't good fusion between the weld and the parent metal.
Right.
The transverse test will pull it apart at that weakest link, revealing a problem that testing only the weld metal wouldn't catch. It's a crucial test for structural welds.
A really vital check for overall integrity, then.
Definitely.
Wow, okay. We've covered a lot of ground today, really foundational stuff for anyone prepping for the CSWIP 3.1 exam. We talked about cold shortness and phosphorus.
The calculation for elongation.
Right, understanding normalizing precisely.
The importance of inner pass temperatures from the WPS.
And finally, what that transverse tensile test actually tells you about the whole joint. These aren't isolated facts. They all build up that bigger picture, don't they?
They absolutely do. And remember, the exam and being a good inspector, it's not just about having the answers memorized. It's about understanding the why.
Yeah.
Why does phosphorus matter? Why follow the inner pass temp? What does that test result mean? Grasping those underlying principles lets you apply your knowledge to any situation, any question. So keep reviewing, keep thinking critically.
Absolutely. So for you listening, preparing for that exam, remember, every single detail, every spec, every test, it tells a story about the weld's integrity.
Yeah.
Understanding those stories is what makes you truly informed and confident.
Well said.
Before we wrap up, here's something to chew on. We talked about how small things, an element, a temperature deviation can lead to big problems. How much focus do you think the industry really puts on preventing these issues right from the start compared to just finding them later through inspection? Something to think about.
Interesting question.
Thanks for joining us on the deep dive. We hope this helps with your CSW 3.1 journey, and we'll be back soon to tackle more essential topics.